Hi, and welcome once again. I hope you know there are links in the description which you can click and open for all the programs I discuss in the video, and I hope you've subscribed. Happy watching. We look at recursion. The topics we'll cover are definition of recursion, advantages and disadvantages of recursion, base case and infinite recursion, and recursion functions for factorial, Fibonacci series, binary search, and sum of first n natural numbers. We look at advantages and disadvantages of recursion. Recursive functions make the code look clean and elegant, and a complex task can be broken down into simpler subprograms using recursion. The sequence generation is easier with recursion than using some nested iteration. These are some of the advantages. The disadvantages are that sometimes the logic behind recursion is hard to follow through. Recursive functions can take up a lot of memory and time, and recursive functions are hard to debug. We look at an important concept, that of base or termination condition. A recursive function has to terminate to be used in a program. It terminates if with every recursive call, the solution of the problem moves towards a base case. A base case is a case where the problem can be solved without further recursion. In the recursive program, the idea is to represent a problem in terms of one or more smaller problems, add one or more base conditions that stop the recursion. A recursion can lead to an infinite loop if the base case is not met in the calls or there is no base condition in the code. We'll now look at recursion for factorial. We'll decompose the original problem into simpler instances of the same problem. For example, 5 factorial is equal to 5 into 4 into 3 into 2 into 1. Similarly, if we have n factorial, we can break it down to n factorial is equal to n into n minus 1 factorial, or n factorial is equal to n into n minus 1 into n minus 2 factorial, and so on. We look at this in a program where we have a function fact which has a single parameter n, and if n is equal to 1, we return 1, else return n into fact n minus 1. When this function starts, if n is greater than 1, function n minus 1 is called, and that starts execution. Now, if n minus 1 is greater than 1, then fact n minus 2 starts, and these steps are repeated till n is greater than 2. The moment n is equal to 2, function fact1 is called, and that returns 1. Once it returns the value of fact1, the earlier steps come back. So we have fact2, which is equal to 2 into 1. The function returns 2. Fact3 will be equal to 3 multiplied by 2, 2 coming from fact2. Fact4 will be equal to 4 into 6, 6 comes from fact3. And all this gets repeated till fact n minus 1 returns its value. That will return the factorial of n, which is n into fact of n minus 1. We're going to look at an example of factorial using a function which is a recursive function called num underscore factorial, to which we pass the value n. We'll also print the value of n each time. And if n is equal to 1, it should return n, else it should return n multiplied by num underscore factorial n minus 1. We'll keep track of n and n, the factorial of n minus 1 each time. And in the end, we'll see what is the result. So when we input the value 5, we are going to look at the output. So we've entered the value 5. So starts with n value 5, then 4, 3, 2, and 1. The moment the value of n is 1, it will start with multiplying 2 by factorial 1, then 3 with factorial 2, 4 with factorial 3, 5 with factorial 4, and that will give us the final output 120. We'll now look at the Fibonacci series. This series was popularized by the Italian mathematician Fibonacci and is generated by adding the sum of the previous two numbers each time. So if we have 0 and 1, we'll get the third number as 1, which is the sum of 0 and 1. The next number will be 2, which is the sum of 1 and 1. The next will be 3, which is the sum of 2 and 1. 5, which is the sum of 3 and 2. 8, which is the sum of 5 and 3. 13, which is the sum of 8 and 5, and so on. So the formula here is Fn is equal to Fn minus 1 plus Fn minus 2 when n is greater than 1. If we have the function Fn, where we'll give a condition if n is equal to 0, return 0, else if n equal to 1, return 1, else the result of Fn minus 1 plus Fn minus 2 is stored in a variable called res, which is returned. Now, if we look at the algorithm, we start with Fn, and if n is equal to 0, it will return 0, go to step 4, where we are going to return F1 plus F0. Otherwise, it will go to step 3, where we call the function for Fn minus 1 added to another function called for n minus 2, and that will be repeated till we reach Fn. So let's look at this with an example. Suppose we have n as 9. So we start with the first step, F9. We'll give a call to two functions, F8 and F7, which will be then giving a call to F7 and F6 and S6 and F5. So this will carry on till n is equal to 1 and n is equal to 0, in which cases it will return 1 and then it will return 0. Once that happens, it will put the values of F1 and F0, add these together, assign it to F2, which will then get added as F2 and F1 and be assigned to F3. And this will continue till we reach F9, which will have the sum of F8 and F7 returned to it, and it will give an output 34. Let us look at an example of Fibonacci series using the recursive function Fibo_series, to which we pass the value n. If n is equal to 0 or it's equal to 1, then it's going to return the values of n. Otherwise, it's going to return the sum of Fibo_series n minus 1 plus Fibo_series n minus 2. It'll store it in a variable res, and it'll return this variable at the end of this recursive function. So the moment we enter the value of n, 9, it's passed to this function, and when we execute it, it will give us an output. The Fibonacci series for 9 terms is 34. We can also take a user input and pass that input to a for loop. In that case, we will generate the entire series using the for loop, and each time the Fibo_series is called, to which we pass the value I. I is in range 0 to num plus 1, where num is the number that the user inputs. When we execute this, we'll see that the entire series is generated, and we don't just get the last output 34, we get all the numbers of the series. We now look at an example of binary search with recursion. This is a search technique where we search for a number in a sorted list or an array by repeatedly dividing the search interval in half. We look at an example of a list of numbers which is sorted, and we're going to find a number within this list using binary search. We'll take an example of a number 75, and here we're going to declare two variables, L and R, which stand for the lowest index, and R stands for the highest index. Note that we've also mentioned the index of each number to make the example more clear. We'll use a variable mid to find the middle index of this list. So we use the formula L plus R minus L upon 2. Here we use floor division so that the answer is a whole number. Also, this formula will make sure that the number will include both odd and even number of indexes. And we compare 75 with the middle term, which is in index 5, which is the number 50. And we find that 75 is greater than 50. So we'll now discard the indexes lower than 50, and we'll consider only the indexes on the higher side of 50, which is 6 to 11. We now repeat all the steps that we did earlier, that is, take L as 6 and R as 11, find the mid of these two indexes, and that turns out to be 8. At 8 index, we have the number 65, which is again less than 75. So we will discard all the indexes less than 65 and consider the ones which are more than 65. And here we have L as 9, R as 11, and we get the mid index as 10. We compare 75 with the number at index 10, and it's turned out to be 75, which means that it will return the index of 75, that is 10. We are now going to look at an example of binary search using a recursive function. The name of the function is binary underscore search, and we pass 4 parameters. The first one is a list. L is the index of the smallest number, and R is the index of the largest number. Key is the number that we are trying to find within this list. Now we check whether the list is not empty, and if it is, then we'll return -1. To do that, we say if R is less than equal to L, return -1, else we find the mid index of this list. In case the number at the mid index is equal to the key, then we'll return that index. Otherwise, if the key is less than the element in the middle of the array, then we start a binary search which will be on the same list, but it will be from index L, the smallest index, to the mid -1 index. And again, if the key is more than or larger than the element in the middle of the array, then it should again start with a binary search on the list, but this time it will start from mid +1 and go up to the largest index. So we're going to divide the list into half each time, and in that case we keep searching only in the half that is relevant for our search. And once we've done that, we'll be able to find whether the key exists or it does not. We input 21, and when we execute this function, we'll see that it will output 21 was found at index 6. Now we look at the sum of n natural numbers using recursion. And once the function starts, it will repeatedly call itself with the next smaller number till n reaches 1, and then it will output the result. We're going to define a function sum underscore num, to which we pass a variable n, which is the number of natural numbers you want to add. If n is equal to 1, output 1 and stop. Otherwise, go to step 3, where we add n to sum underscore num n-1 and call that function sum underscore num n-1. We repeat this step until n is equal to 1, and then we output the result. We're going to look at a function sum underscore num, which is a recursive function to find the sum of the first n natural numbers. We check if n is equal to 1, it should return n. Otherwise, it will return n plus sum underscore num n-1. Now, if we input the number 10 here and execute this function, we'll see that it outputs, you have entered the number 10, and the sum of the first 10 numbers is 55. We now look at the base case of each of the examples that we discussed. The factorial function has the base case n equal to 1. This makes sure that the recursion stops and the output is given. In Fibonacci series, we had two base cases, n equal to 0 and n equal to 1. These made sure that the recursion stops and the output is given. In the example for binary search with recursion, we had a condition: if r less than equal to L, return -1. In this case, if the index of the largest number is less than or equal to L, it means that either the list is empty to begin with, or the key was searched in the entire list and it was not found. So this condition will return -1 and the search will stop. In case of sum underscore num, the function had one base condition where n equal to 1 stops the recursion and gives the output. So that was a little bit about recursion. I hope you understood. You can always click on the links in the description, and I hope you keep watching. See you soon.